This is Wenjun speaking, a professor of Wuhan Textile University in China. It's wonderful for me to share our research. We preface a microwave strategy for structural engineering of clean energy materials. So this presentation will be in three parts. The research topics will cover the study of novel modification engineering and universal preparation technology. So firstly, I will give you the background of our research. So we can see these pictures. This is the comparison of optical valley in Wuhan in the past 10 years. With the rapid development of social economy, environmental pollution has gradually become a global issue. So in order to replace the traditional energy, people are developing new materials and new energy conversion and storage technologies. So as we know, the optimum preparation of electro materials is the key point, whether in energy storage or electrocatalysis. So presently, a variety of electromaterials can be prepared by various methods, but there are some common problems, such as complex process, long-term and high consumption. So we wondered if we could develop a new strategy for the simple, faster, and universal material synthesis. So microwave as a kind of long witness electromagnetic wave, so has the advantages of rapid, high energy, simple, and universal and controllable. So it can react with matter for energy conversion through three mechanisms: dipole loss, conduction loss, and magnetic loss. So our objective is to better combine microwave properties with the structural engineering of materials. So try to solve some problems such as how to combine with other mechanisms or technologies, and how to be more controllable and how to be beautiful. So, well, how does microwave work in our real situation? First, I'd like to talk about the novel modification engineering use microwave. Atrombic niobium pentoxide has been widely used as the electro material in energy storage due to its high capacitance and no phase transition occurs in charge and discharge process. However, it has no conductivity. So commonly, the introduction of oxygen vacancy can improve the conductivity of oxides. So we think whether the conductivity of niobium pentoxide can be increased by introducing oxygen vacancy by microwave. So GO and niobium pentoxide were mixed together by ultrasound. Then the oxygen vacancy can be introduced by microwave combustion after freeze drying. So because of the reducibility of carbon NGO, the XPS of the oxygen element after microwave reaction will show an obvious peak of oxygen defect. So these phenomena are universal to other oxides, such as vanadium oxide, tungsten oxides, and so on. So this sample could show approximate theoretical capacitance. So then, next, we think how to combine microwave with other mechanisms. So one day I found a very interesting performance in two papers. Active metal particles can age the surface of carbon-based materials at high temperature. So that's a magic thought came to my mind. Whether the instant controllability of microwave can be used to prepare uniform powers materials. So we selected silver nanoparticles as the active metal particles, which are easy to form the round particles. By etching graphene on the microwave, we can design porous graphene. So as shown in the TEM images, the pore size of this porous graphene is very uniform and even beautiful. Then through the mechanism verification, it is confirmed that the active metal under microwave could catalyze oxygen atoms to H carbon atoms. So moreover, we can also realize the judgment of pore size and the universal preparation. The porous graphene with different uniform pore size could show excellent performance in salinity gradient power generation. So secondly, except for the modification engineering, I'd like to talk about the universal preparation technology using microwave. So in our previous work on the introduction of oxygen defects in oxides, we found that with further reduction, the corresponding combines were gradually formed in the products. Although these transition metal carbons have many excellent properties, their conventional synthesis methods usually require a long-term high temperature or etching process. So we directly use microwave pulse to deeply reduce the oxide nanoparticles. So by changing different metal precursors, these methods can prepare 6 kinds of combined nanoparticles located on the surface of graphene uniformly. So actually, since carbide is a kind of annoying, so we consider whether the oxygen atom will be directly replaced by the carbon atom, or will it reduced to elementary substance and then be carbonized. So it turns out that the carbide is a gradual transformation rather than a direct substitution. So furthermore, in addition to the ordinary nanoparticles, we can also use microwave to prepare ultrafine combined nanodots. So because of the uh, universality of microwave, we can also one step in doping. So this ultrafine nut size and uh, doping regulation could exhibit high kinetic activity in hydrogen evolution. So next, in addition to zero-dimensional combines, two-dimensional combines with high specific surface area can also show excellent kinetic activity. However, the max etching methods requires dangerous acid, and the CVD methods faces stricter conditions. But in China, there is a folk art of melting sugar by heating and blowing it to get different interesting shapes. So we thought about how to combine sugar blowing with microwave to prepare two-dimensional transition metal carbines. By choosing the suitable carbon source, the metal source, and forming agent, we finally successfully prepared a two-dimensional tungsten carbide on the microwave pulse. So because of the insert analysis of microwave, 3 processes of polymerizing, bobbing, and burst can be clearly observed. So the two-dimensional tungsten carbide exhibits single crystal structure. So, additionally, this fast, controllable, green, and commercial potential microwave strategy can propel a variety of carbides. Due to the terminal modification of ultra-thin carbonyl, these two-dimensional carbides can achieve suitable hydrogen evolution. Okay, so is the conclusion and outlook. So in recent years, our team has conducted a serious studies on clean energy materials using microwaves, such as defects, crystal structures, and so on. We are very pleased that some of our original explorations have been recognized by peer review. Then we think what's next? We are going to think what's after the microwave combustion and what's after the microwave discharge, and how these high performance nanomaterials can be used functional and intelligent textiles. So, sincerely thanks to the committee, we believe that microwave technology can bring surprise to more fields. So thank you for your attention. Thank you.